All right. Hey, everyone. Good morning. Math 162, week 8, lecture 1. Not too much time left in the semester. Things are, I'd say they're winding down, but can't really say that. They're staying as high pace as they've ever been, and it'll just keep going until our last day of class. Just reminding you of a few due dates, 7-1 and 7-2. We had finished last class, so they're due on the 15th. And then 7-6, we are going to knock out today, so that will be due on the 20th. The next class will finish 7-7. Fair warning, the next test is not going to just be on chapter 7. It will include chapter 7 and 11. We're going to temporarily skip over chapter 10. I'll talk about that more next time. But before we get into 7.6, where we start our discussion on vectors, which is an awesome field of mathematics, it opens up a whole, just entire field of things we can do that I'm not going to expand upon. I want to point out, and this is unfortunate, but this is just how things go. Due to circumstances, I will not be able to host a Zoom class live on Thursday the 15th or Tuesday the 20th. Something came up, unavoidable, you know how it is. But the good thing is with this format, I don't have to fight to get a substitute teacher and lose class time. I have already pre-recorded everything and packaged together something, and it will be on YouTube actually no later than this evening. So if you wanted to get ahead, you absolutely could. But if you don't want to watch those until the 15th and the 20th respectively, or whenever it is that you watch them before class on the 22nd, when things will return to normal, then you can do it on your own schedule. But you will be responsible for watching those. Again, you'll see the normal whiteboard introduction with dates, you'll see all the material, and then we'll close up shop per usual. You just won't be able to ask me questions live because it won't be on Zoom. So any questions that you have during that, as always, you can email me and we can discuss it. If it needs to go past email, then we can work on that as well. And again, I do apologize for this, but I figure this is at least the best of the situation. It will be available again in YouTube. I'll have those linked in Canvas, of course, just like all the previous lectures. But as always, if you just go to my YouTube page in the Math 162 Summer 2021, you can find them there as well, again, once they've been uploaded. I've recorded everything. I spent the last 48 hours just really, really overdoing it because I had to do this for 3 classes. And yeah, so I think it was one of our classes, the introduction, I might have said something that was slightly wrong and I come in and correct it later, but it's not the end of the world. It was a very minor detail. So just bear with me on that. But everything in terms of material is fine. But yeah, all right, so again, we're gonna work on 7.6 today. It's a pretty lengthy section, so let's go ahead and get into it. I will be available for questions in chat today, of course. It's just, we won't have the Zoom on the 15th and the 20th. So that's when it'll be different. All right, here we go. 7.6 vectors.
Let's give ourselves lots of space. I feel like this section has changed section numbers more than any other in this entire course over the past, but not that that matters to y'all. All right, so we're going to start talking about the vector, what it is, what it means, what it's about, how do we use them, what can we do with them, and we're just going to kind of have an introduction with this. We will do a couple slightly more advanced things with them, but we will not even come close to touching everything that we can do with vectors. So first of all, let's compare the idea of being a scalar to the idea of being a vector. So a scalar only has size. It's a number that only has size, but a vector is a number that has size and a direction. So a number like 3 would be a scalar, but saying something like 3 east, and I'm spelling it wrong, that would be a vector because it has size, the number, and a direction east. Now, we usually don't use north, south, east, west as our directions. Usually we'll say they point up or right or left or down. which would be the equivalent, or maybe we use degrees, maybe we use angles or radians to indicate direction. So another way of comparing a scalar versus a vector, if someone says that they are driving 55 miles an hour down the highway, 55 miles an hour is a scalar because it says how fast they're going, but it doesn't tell them what direction. But if you said I'm going 55 miles an hour directly north, that would be a vector because it has speed and direction. So these vectors, we draw them as arrows. So we tend to draw them as something that looks like this, where we call the dot the initial point, where it starts. And then the arrow is pointing. Now, this arrow is no longer representing that it goes forever and ever and ever. The length of this thing correlates to the size of the number. So again, this arrow is not saying that it goes on forever and ever. That's not what we're saying here. We're saying that right here, if you wanted to put another point there, you can. We just usually don't. We would say that's the terminal point. So that's the first kind of different thing, is that we're used to arrows on graphs, meaning that that pattern just continues forever and ever and ever. But with vectors, the arrow is ending at a specific value. So do they have to point up and right? No, they can point up and left. They can point down and left. They can point down and right. They don't have to be all the same length. They can be longer or shorter. And all these vectors represent different values in different directions. The length of the vector is what represents the size. So the longer the vector, maybe the faster you're moving or the more distance you're covering. All right. So we can find J. We can find, why is this thing stalling right now? Which is also known as the length of the vector by Pythagorean theorem. We know the directional components. In other words, so we got a vector that starts here and ends here. All we're doing is saying, if you got a little right triangle, if you know how far to the right you're moving, and if you know how far up or down you're moving, so if you have these horizontal and vertical components, as I said, then you could call the vector, maybe that's C, you can just go a squared plus b squared equals c squared. Quite often, we'll be given the components and we need to find the length or magnitude of the vector. So we know we went 5 miles east and we know we went 7 miles north. How far did we actually go from our starting point? Yeah, we went 5 miles east and then, what did I say, 12 miles north, but someone could get there a lot quicker just by going from the starting point and following the hypotenuse of that path. And they get there quicker. Instead of going 5 and then 12, they might just go like, I don't know, 13 miles. The I don't know there was sarcastic, by the way. So we have some notation, and it looks like this. And what I'm trying to emphasize here is a bolded letter between two lines that kind of look like absolute values. So please note that that is bolded. So this is one way of representing the magnitude of a vector. So an absolute value is kind of like a magnitude. An absolute value is just a length from 0, whether you're going left or right, whether you're going to the negatives or the positives. So like 5 is 5 from 0, or -5 is 5 from 0. But that's only in 2 dimensions. When we're talking about 3 dimensions, sorry, that was only in 1 direction actually. When we're talking about 2 or 3 directions, we use two sets of absolute values to represent a length in multiple dimensions. So this is one version of it, and another version of it is this. It's still the double absolute values, but instead of a bold letter, you use a regular one, and you put a little arrow over it. Now, I more often than not use the arrow notation so I don't throw you off, because it gets pretty tedious to emphasize bolding with a blind pen. Some people don't do the arrow exactly like that. Some people will do what I call just a top half arrow like this. This is my favorite way of doing things. So some people just do that. Some people put the bottom half of the arrow on it as well. It doesn't matter. They mean the same thing whether it doesn't have the other piece or not. So these are the magnitude of vector v. See, we represent the vector with the arrow over it, or bolded. So bolded things or things with arrows are vectors. Things that aren't bolded or don't have an arrow over them are not vectors. Okay. If you're given 2 points, find the x and y components, aka their lengths. Just subtract their coordinates. Subtract, subtract. In other words, you're doing x2 minus x1 and y2 minus y1. That would give you the a and the b in that little triangle before. So I might tell you that I've got a vector that starts at 2, 5 and ends at 13, 7. Then you can figure out how far right and up or down it moves, or left and up and down, whichever it might be. If you're Jen, this thing is killing me right now. I typed given. If you're given 2 points and your computer doesn't freeze up on you, you can just subtract their coordinates to find their lengths. And one last statement before we get to some actual math. 3 asterisks. 2 vectors are the same. Their magnitudes, directions are the same. Magnitude meaning length, direction meaning angle. So what we're going to do with example 1 is we're going to kind of put all of this stuff together. We're going to find some magnitudes of vectors. We're going to find their directions. And we're going to do it in kind of a weird way. But it works. And then we can prove that 2 vectors are the same or not. What I'm saying here is, actually, let's not point them up and left. Let's point them up and, let's point them up and left, not up and right. Here's a vector. This is v1. Here's another vector, and I'm not sitting at the same point, but I'm trying to draw it in such a way that the lengths are the same and the directions are the same. So if v1 and v2 are the same length and point at the same angle, then they are the same. Because here's the thing about vectors. I can take this vector right here, v1, I can pick it up and I can transpose it somewhere else. I can put it over here. As long as I point it in the same direction and I make it the same length, even though I've taken this thing and I've moved it way over here, it is exactly the same. So you get a lot of freedom with vectors. You can choose where to start them. It's just they end wherever they have to end based on wherever they started. So if I was doing this on, I just don't want that arrow stuck up there. No, not save yet. Erase, please, and thank you. Thank you. There we go. That's what I want left over. So just taking that thing and moving it all the way over here, they're the same. But these two are the same. I've tried to draw them so that they are the same. So if you've got something, I'm going to erase all this in a minute. But if you've got a vector that starts here and it does this, if that length is 1, and let's say that's a 45-degree angle, if that's V1, I can take that and I can move it over here. I could instead choose to start it there as long as I make it the same length and angle. That's the same V1. Or maybe I choose to put it down here. And as long as I make sure that it's exactly the same length and angle, that's the same vector. This would be the same vector. That one looks a little flatter, doesn't it? That would be the same vector. I can draw this thing a million times. It's just a matter of where do I want to put this thing? Why would I want to put it here? Maybe I want to start it at the origin. That's a pretty common thing, starting things at the origin to make the numbers make a little more sense. We're going to take some vectors and we're going to stack them. We're going to go head to tail, and then another one maybe here, and then maybe another one here. So you might have 3 vectors just littered all over the place, but for mathematical reasons, it would make sense to just go tail to head to tail to head to tail to head. Clickety, 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 clackety, click. There we go. All right. Finally, example. Example 1. Prove the 2 vectors are the same. And I'm going to draw up an axis. And over here at -3, -3, I'm going to have the tail of a vector. And I'm going to have this point set 0, 3. And then I'm going to have another vector. I'll do it in blue. And I'm going to start this one at the origin. And I'm going to have it point at the point 3, 6. So we got V1 and V2. Now, they look pretty resemblant of each other. They look pretty resemblant of each other. It kind of looks like I just drew 2 parallel lines. They kind of look parallel, but just because they look parallel doesn't mean they're parallel. You would have to prove that in some way. Parallel. Maybe we can do something with that. Now, I did not label these points initially, but we can go back and label them. This is at -3, -3. That's the tail. Then the head of it, the arrow, is at 0, 3. This point right here is at the origin 0, 0, and this one is at the point 3, 6. So to prove that these 2 vectors are the same, we need to prove that they have the same length and that they have the same direction, the same angle, the same slope, maybe. Since we just mentioned parallel lines have equal slope. That would be a great way of doing this. All right, so for vector 1, I wish I'd done this in blue and red, but that's okay. For vector 1, we have the x length, how far left or right it moves, as the difference of the x values. This x value is 0. This one is -3. So we're going 0 minus -3, which is 0 plus 3, and that's 3. The y length is the difference of the y's. It ends at 3. It starts at -3. So we're going 3 minus -3, which is 3 plus 3, and that's 6. So this vector means wherever you start, you go right 3 and up 6. That's kind of like the rise and the run in backwards order. Run, rise. So its magnitude, we can do by Pythagorean. If a squared plus b squared equals c squared, these are the a's and the b's. You just do the square root of that. I'm going to give you that as an official formula coming up. But that would be the 3 squared plus 6 squared, which is 9 plus 36, which is the square root of 45, which is 9 times 5 under a square root, which is 3 square root of 5. For the second vector, the x length, now we're looking at the blue one. It ends with an x value of 3. It starts with an x value of 0. So we go 3 minus 0, which is 3. Ooh, those match. That's a good sign. The y length, we ended at 6 and we started at 0. So 6 minus 0, which is 6. Huh. The fact that the x components match and the y components match, honestly, in some teachers' books would say that actually proves that the vectors are the same. Because if their x and y components match, that means they have the same rise and run, which means they have the same slope, which means they have the same length if the rise and the runs are matching. But we are trig students. We are supposed to be a little more technical and actually prove that the numbers themselves are the same. So the magnitude of vector 2, again, that's just what all these extra symbols mean. The arrow just means it's a vector. The ones and the twos are just distinguishing between the first vector and the second one. The double absolute value says find the length. So that's the square root of 3 squared plus 6 squared, which is square root of 45, which is ultimately 3 square root of 5. This length matches that length, so they're the same length. So the magnitude of V1 is equal to the magnitude of V2. What about the directions? Well, I already alluded to this earlier. If they're parallel lines, then they have the same slope. And direction. Now, if one vector is pointing up and right and the other is pointing down and left, they might be parallel lines, but not the same vector because they're pointing opposite directions. So just be careful. They have to make sure your arrows are pointing the same direction. Well, the slope of the first line, we're just doing y2 minus y1 over x2 minus x1. So that's 3 minus negative 3 over 0 minus negative 3, which is 6 over 3, which is 2. Again, it's the same y and x components before. Those are the rise and the run, which here we have the rise and the run again repeated. The slope of the second line, well, again, we already see those numbers matching, so it's a good sign. But using the coordinates, you're doing 6 minus 0, 6 minus 0, and then 3 minus 0 in the bottom, which is clearly 6 over 3, which is clearly 2, and they're the same slope. So V1 and V2 have the same length, the same magnitude, they have the same slope, so the first vector is equivalent to the second vector. That's our conclusion. Is there another way to prove they're in the same direction? Yes, we can prove it based on angles. We can, call these little triangles and then figure out this angle theta based on sines or cosines or tangents, and the same thing here, and you could prove that those angles are the same. There are many different ways to show this. In fact, as I've already said, some simpler-minded trig teachers, maybe if this was just a geometry class and you were doing vectors instead of a more advanced class, they could say since you prove the x and y lengths are matching identically, that's good enough to say they have the same direction and distance. But we just want to be a little more meticulous with this. Okay. So this blue vector is exactly the same as this black vector. They are the same thing. Maybe it's better to start at -3, 3 and end at 0, 3, or maybe it's better to start at the origin and end at 3, 6. Maybe it's better to start that vector right here, make sure it goes right 3 and up 6 and ends here. That could be a third version of that vector. I will say the first thing we usually like doing is starting one at the origin. If you've got multiples in there that we're adding or subtracting, that's when we start going head to tail kind of thing. But we're not going to focus too much on that for now. Let's move on to the next idea, which is a scalar multiple vector. So if I give you a vector and then I say, well, what's 3 times that vector? Or what's 5 times that vector? Or what's 17 times that vector? Or what's -1 times that vector? What does it do? Well, a scalar multiple of a vector just changes the length of the original vector. So 2 times a vector doubles it. Half times a vector would half it. 10 times a vector would, you get the idea, multiply it by 10. It would still point in the same direction. So it doesn't change how it points, it just changes how long the line is. However, I did mention a negative in there. What if there is a negative? Scalar is negative. It rotates the vector 180 degrees, i.e. points opposite. So let's say I had this vector right here. This is our vector v. Let me put the label above it. Not that it matters. There's our vector v. If I wanted to represent the vector 2v, it would point the exact same direction. It would just be twice as long. So I'd have to figure out how long this is and then just double it. Or if I know this goes right 3 and then up 1, just do that again, right 3, up 1, and boom, you've got your doubled vector. So I want to make sure that looks like about one of them. That looks like about 2 of them. So again, right here, let's just say from here to here was the length of v, the original v. From there to there. So then you have another one as well right here. They point in the same direction, just one is doubled. Or what about a half of v? Half of the original vector. So it still starts at some arbitrary point, it will still point in the same direction, but now it's going to be half as long as this one. So probably about something like that. So again, if I doubled it up from end to end, that whole thing would be v. If I ignore the arrow section here, if I had the black and the blue, that would be a full length of v, but we have half of it, which is why it's half as long. And then finally, what if we had negative v? So now we start at some point. So starting point is arbitrary. But now instead of going right and up, we're going to go left and down, exactly in the same parallel direction, ignoring going up and right or down and left. But now instead of putting the arrow on the up and right, we put it down and left. So like this, that looks a little too steep. Let me try again. So something like this, that looks pretty good. But that would only be the half distance. We got to make sure we try and match that length as best as I can. Good enough. So again, some of the things I said out loud that I'm demonstrating with these images, given a vector, leave some space for me to write the v afterwards. 2 times that vector, double the length. 1/2 times that vector would half the length. And we already said the -1 just points it in the opposite direction. So given a vector v, 2v would double it, and then a half of v. Let me just write the 1/2 there, so it doesn't look funny. Sometimes my pen does weird things when I hit a button. There we go, semicolon. So given some vector, a 2 in front of it doubles the length, that's all it does. A half in front of it halves the length, a negative in front of it switches direction. And you can have combinations. I could do -2v, which would point this way, but be twice as long. I could have -3v, and it would be 3 times as long, pointing this opposite direction. All right. How are we on time? Not too bad. Next up, unit vectors. I have this underlined. Unit vectors always have a length unit, excuse me, unit vectors are absolutely critical. They are the basis of us actually being able to write vectors in component forms. Component forms being the X and the Y breakdown. Because we can write vectors in 2 different ways. We can write them with their components, saying that, hold on 1 second, saying that we're going to go this far in one direction and this far in the other direction. Or we can talk about them based on their lengths and the angles that they point at, as we'll get to later. But to go between them, this unit vector is an important concept. And a unit means just absolute bare bones 1 in consideration of whatever system we're in. So when we say the word unit, we mean 1. So we're talking about a vector that's 1. Well, the angle is 1? No, that doesn't really make any sense. The length is 1. So a unit vector is a vector that has length 1. These are what make up the basis of being able to do a lot of things in this section with vectors, and multiple sections, in fact. There are 2, there are 2 very important vectors. I, lowercase I, and j. Or some people put them with little vectors over them, more appropriately, I like this, and j like this. Like instead of a dot, you put arrows over them. Or you just bold them. Really, really, really emphasize that. And you can see why the bolding is just terrible. I mean, it's very easy. In fact, I thought I hit bold when I did that. There we go. Got that. 2 very important unit vectors, I and j. I and j. Now, I is something we kind of started using with the complex number system, where I represents the square root of -1. That's not the same here. What's interesting is that this stuff does eventually start pairing with complex mathematics with the imaginary number system. And what's really interesting is that the j vector usually ends up representing the amount in the complex number, which is I. It gets kind of convoluted, but we don't need to worry about that for now. So what are our unit vectors I and j? We need them to represent a unit in each of the x and y directions. So in order to talk clearly, in order to represent these vectors almost like a coordinate, we have to have these i's and j's because that's what represents an actual arrow. When we write something like 2 comma 3, that doesn't say to point a vector at 2 comma 3, that's just the point 2 comma 3. It's not the same representation. We can say there's a vector formed by 2 points, but then we have to label both of them. So the I and the J, let's call this right here 1 on the x-axis and this right here 1 on the y-axis. I, we traditionally start at the origin, doesn't have to, but that's just traditional. And we point it completely horizontal at the 1 on the x-axis. So we're going from 0 to 1 completely horizontally, which means it's a length of 1. That is the I vector. This gives us just something to count off for the x directions. I bet you can probably guess what the j vector is. You start at the origin, and you just point up to 1 on the y-axis. That is the j vector. Now, we typically see these so often with vectors that if you don't bold them or don't put arrows over them, that's perfectly fine. So we're a little lenient with this, whereas even though the i's and the j's are supposed to represent vectors, if you don't bold them or if you don't arrow them, we're still going to count it correct. Now, my i's, I really like to bend to the right. My j's, of course, are bending to the left, but it's pretty easy to confuse these two if you just make them as straight as possible. If that's your I, you can see how that could very easily just get confused with a J. So make sure you know what your I's and your J's are. So again, this is going to help us break things down into component form. Right. So with these I's and J's, we can represent any and every vector with scalar multiples of I and J. Stop capitalizing. Where we have a standard form of a vector being AI plus BJ. And I am bolding the I's and J's. Again, if you don't bold it, I'm not going to count it wrong for I's and J's. But they really should be. For A, we're bolding the X component, and B is the Y component, the original vector. V. So A is just how far right or left you move, B is just how far up or down you move. A lot of people will look at this stuff and kind of lose their sense of where they are. Oh, I's and J's, oh, new letters, that's got to complicate things. Really, the math here is nothing new. We're kind of done introducing trigonometric concepts at this point. We will kind of blend them, what we've already done, in with this idea of having a direction pointing in certain ways. But we're not going to actually teach you any new trig. This is not trigonometry. This is a new field of mathematics in itself. But without trig, you can't do vectors. All right, so where we have A and B giving us the components, how far left, right, up, or down to go. Also, where the magnitude of bolded vector V or arrow on top of it is double absolute value. I'll put the arrow since I'm writing this by hand now. The magnitude of any vector is going to be the square root of a squared plus b squared. And that's because, let's just say you have say you start at the origin, and you go right based on A. You go up based on B. Starting point, terminal point. That C is just based on Pythagorean, A squared plus B squared equals C squared, where C is the magnitude of the vector. The hypotenuse of these little right triangles you can create is always the magnitude. It's always the length. So when you're in standard form, start vector origin. This is just writing down what the drawing to the right says. You can start your vector at the origin, then A and B give the X and Y coordinates, the terminal point. Standard form is where it's at. You can start and end a vector wherever you want, but when we want to break it down to simple term as possible, we just want to know the X component length, the Y component length, so that way we could put it at the origin and make it a lot simpler. That's what standard form represents. And again, the I tells you how far right or left to go. The J tells you how far down or up to go. So let's try this out finally. Example 2. Write the vector standard form given by A. We're going to start 1, 5, and our terminal point or ending point is going to be 4, -7. So again, you could certainly draw this up. You can, and I'm going to erase this in just a minute, but you can start over here at 1, 5, and then at 4, -7. And your vector looks like something like this, but I can't clearly see the X and Y components. I can certainly just measure them. I can, figure out how high this is. Whatever this distance is the Y component. Whatever this distance is the X component. And that's all it is to it. But if we take this vector and move it in such a way that we start at the origin, so I'm here and then pointing down and right, then that X and Y coordinate where it ends give us the A and the B that go in front of the I and the J. So the X component, which we call A, is the difference of the X coordinates, 4 - 1, which is 3, and you have to go ending minus the starting one. You cannot swap the order for vectors. That is critical. So there's your X component. Your B is the difference of the Y's, which is ending -7 minus starting +5. -7 - 5 is -12. That's it. That's the entire process, besides just putting the 3 and the -12 in front of the I and the J. So our original vector V is represented by 3I minus 12J. And again, if you're just writing the vector V equals 4I minus 12J, that's okay too. Because I and J are supposed to represent unit vectors. So it's implied that they're a vector. So that says to go 4 in the X direction and 12 down in the Y direction to get your terminal point, no matter where you start. So if I start at 1, 1, go right 4 down 12. If I decide to start at 2, 1,000,000, go right 4 down 12. There's your vector. I did not ask for the magnitude, so I don't need it, but if I did, you would just go square root of 4 squared plus 12 squared and get whatever that answer is. B. Let's do another one. Let's say that we start at -4, comma, -3. Looked like a comma, and I didn't mean for that. And that we end, or our terminal point is, long pause, 8, -2. So to find this in standard form, we just subtract the y's, subtract the x's, and that's pretty much it. So the a value is the difference of the x's, terminal minus starting, so 8 minus -4, which is 8 plus 4, which is 12. The b is the difference of the y's, -2 minus -3, which is -2 plus 3, which is +1. That means our original vector in standard form can be represented by 12i plus, do I really need to write this 1? No. 1 times j is just j. You can write the 1, but my math lab will probably mark it wrong on a test. If you point that out to me, I'll give you credit for it, sure, but on a homework, you'll have to do it again. So we don't really need to write this 1. It's implied because it's in front of something else. So again, traditionally, we don't write that 1. It's not simple with the 1 times something there. And again, if you just wrote that the vector is 12i plus j, that's okay as well, without the little arrows or the i's and j's being bolded. Nothing crazy. We subtracted. Oh no. Terrifying indeed. Again, if you wanted the magnitude, it would be the square root of 12 squared plus 1 squared, which is the square root of 145. And humana. I don't think that breaks down, but I didn't ask for it, so I'm not going to do it. All right. So we talked about how we can take a vector and just shift it to the origin and get the numbers for the x and the y components really easily. We've talked about how we can get the size of these vectors pretty easily. We've talked about what happens if you put a number in front of the vector, how it doubles it or halves it or triples it or whatever, or makes it face the opposite direction. But this was all dealing with a single vector. What if you wanted to take 2 vectors and add them, or maybe subtract them, or multiply them? Question mark. Let's see what we get to in that, because there are 2 types of vector multiplications. That's probably the first time you've ever heard that there are 2 types of multiplications of something. I'm pretty sure you probably have never heard that before, unless you've dealt with vectors before. But under normal numbers, even with imaginary numbers, there's only one kind of multiplication. Well, Mr. Beckner, distributing versus foiling, it's all the same. I'm talking about doing one thing that gives you answer A versus doing something completely different that gives you answer B. And I'll even spoil the names. They're called dot products and cross products. And they are completely different. One of the answers is a scalar, one of them's a vector, one of them we won't even do in this course. But we'll save that for section 7.7. I did call this 7.6, right? Nothing with 8. I did, good. I think I mentioned earlier, this section has changed numbers quite a lot. All right, so now let's deal with 2 vectors. We can add or subtract them quite easily. 2 vectors, u and v. Oops. Whether they're bolded or have the arrows. As well as multiply them by scalars quite simply. And when I say quite simply, I mean just do the arithmetic as it looks, combine like terms, distribute. That's it. There's literally nothing new to teach you here. In other words, given some vectors u and v, I'm just going to write the rest of this. We could find 3u pretty easily. We could find u plus v pretty easily. we could find 6u minus 5v pretty easily. The only thing that we really have to worry about is handling the scalars first. Why? Because PEMDAS. That 3 or the 6 or the -5 up there is a distribution, and we distribute before we combine like terms. PEMDAS, multiply before adding and subtracting. Again, most of this section and the next section is not really anything new. It's just writing it in a slightly different way. Now, again, I'm not saying that we're always finding 6u minus 5v. I'm just giving you an example of what I could ask, and that it's really just basic arithmetic with some i's and j's in there. All right, so next example. Example, what are we up to? 3? Yes. Given, let's say, find the requested item given that vector u, and they don't have to be letters u and v, can be any letters in the whole world. These are just tradition. Vector u, let's say, is 5i plus 3j. And then let's say vector v is going to be 9i minus 2j. So for A, what we're going to find is 3u. Again, just arbitrarily the same number. I could ask for 4u or 12u or 2u or a half u, whatever. All we do is we take the vector u and plop a 3 in front of it. Here's the vector u. Put a 3 in front of it, distribute. 3 times 5 is 15, so that's 15i. Plus 3 times 3 is 9, so that's 9j. That's it. Crazy stuff right here. Man, why wasn't this something we did first day of class, right? Well, don't worry, we'll start invoking that trig stuff into it sooner than later. B. Let's do -2v. Now you have to pay attention to which vector we're supposed to be manipulating. So that says v, so we take this one and plop a -2 in front of the whole thing. Oh my lord, this is awful, right? Well, it's just watching signs and distributions and numbers. -2 times 9 is -18, so that's -18i. -2 times -2 is a +4, so it's a +4j. And that is the entire problem. So this vector for B would be twice as long as the original V, but it would also point in the opposite direction. And you could certainly draw these up, and starting at the origin would really help you to illustrate that fact. If you drew V going right 9 and down 2, then you could draw the -2V, which would go left 18 and up 4. And it would be really easy to see that that vector is just twice the other vector and pointing in opposite directions. This would have been the V, this would have been the -2V. Again, I didn't ask for the illustrations, so I'm not leaving them up there permanently. I'm just saying that if you doubt this, maybe the visual aid would help you. And we are not on B, we are on C now, which is U plus V. So just take the vector U, which is 5i plus 3j, and then add the V vector, which is 9i minus 2j. Make sure you can tell the difference between your i's and j's, because then you're just combining like terms. Nothing new in terms of concept. 5 plus 9 is 14, so that's 14i. 3i minus 2j is 1j, so we don't need to write the 1, we just write a j. So 14i plus a single j. So that says we go right 14 and up 1. So instead of moving u, and then from where u stops, moving v, you can just instead move right 14 and up 1. I will demonstrate C after I finish D, because it's an important concept. Are we on time? 15 minutes? Okay. D, for you, minus 3v. So this is going to be 4 times the vector u, which is 5i plus 3j. Then a minus 3 times the vector v, which is 9i minus 2j. Again, I know some of these are starting to look like dots, but if you really zoomed in, you'd see these mini arrows. Well, distribute first for obvious reasons. 4 times 5 is 20i plus 12j. 4 times 3 is 12. Make sure you're distributing the minus. So that's negative 3 times 9 is negative 27i. Negative 3 times negative 2 is a positive 6j, which will give us a final answer of 20i minus 27i is negative 7i. And then 12j plus 6j is a plus 18j. All right. We got right 14. We don't really need to go up or down very much though. And yeah, just a real right heavy graph here. So the vector u was the 5i plus 3j. So that's right 5 and up 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So here's 14. So right 5, 1, 2, 3, 4, 5. So here's 5. And then up 3, 1, 2, 3. So in blue, I'm going to do the vector u, which starts here and ends here. So here is the vector u. Here in red, I will do the vector v, which is the 9i minus 2j. So right 9 down 2. 1, 2, 3, 4, 5, 6, 7, 8, 9. So right 9 and then down 2. So starts there and ends there. As best as I can. Here's my vector v. Let me just put the 9 up there. Now what we found was u plus v, which turned out to be 14i plus j. So let's draw that one in a different color. Let's go with, I don't know, black. That works. 14i plus j. So that's right 14 and then up 1. So here's the ending point if we start at the origin. So this vector right here, which is pretty flat, that right there represents u plus v. Check this out. Check this out. After you drew u, from the ending point of u, draw v. So yes, the standard position origin puts it here, and I forgot my arrow. That's my bad there. But instead of drawing it at the origin, let's draw it from the very end of u. So we're going to go right 9 and down 2. So we're starting at an x value of 5. When we go right 9, we end up at 14. Then we're supposed to go down 2 because of the minus 2j. So when we go down from a height of 3, we end up at a height of 1. So this right here is also vector v, just not drawn in standard position. And look what happens. If you draw u, then draw v, you end up at the same point as u plus v. So that demonstrates the geometric side of vectors, how you can find out where they end without doing any of the math that we actually showed you here. So if I didn't do any of this, I could figure out u plus v by drawing u, then from where u ends, draw v, and then that point gives me the components a and b of u plus v. So you can do this as a geometric argument, or you can do this as an algebraic argument. But geometrically, the sum of two vectors is just drawing one and then draw the other from the tail of the first. So in terms of graphing, adding two vectors means to draw the first and draw the second from the terminal point of the first. This will give you terminal point sum. If you wanted to subtract them, that just means that the v is going in the opposite direction. So, and this is less interesting for us. You would draw the u, and then you would draw the v, but the opposite direction. So instead of going right 14 and down 2, you would go left 14 and up 2. So if I went left 14 and up 2, I'd end up over here at, what's that, -9, comma 5. This, then this would represent the vector u minus v. Again, not that interested in that for now, which is why I'm going to erase it. But at least I've said it in a recorded scenario. But it's just because you're changing the direction of v, and then you're adding it basically from there. So you just change the components, you take the opposite of the components, and then add that to the v. So you stack it after you face the direction, opposite direction. All right. 10 minutes, 10 minutes, 10 minutes. How much can we get through? Yeah, we can do this. Unit vectors. Wait, you already talked about unit vectors. Unit vectors in any direction. I want to actually underline this. Go. Unit vectors in any direction. So we talked about how I and j are unit vectors and how they're important, because if we have 5i plus 7j, it just says go right 1, 2, 3, 4, 5, and up 1, 2, 3, 4, 5, 6, 7. And that's the basis of our little right triangle where the vector is the hypotenuse. And then you can just get rid of that part and boom, you're done. There's your vector. So i's and j's are awesome because we really like breaking things down in terms of just left and right and just up and down. And i's and j's do that for us. Well, here's the thing though. In the real world, not everything that we measure is best measured just left and right and just up and down. Sometimes we do a rotational coordinate system where maybe this is your x-axis and this is your y-axis. Or sometimes we have one of the axes skewed but not the other. So maybe this is your y-axis and this is your x-axis. There can be lots of reasons to do this. If you have a moving system, a rotational, if it's moving in a cylindrical way, in a circular way, quite often we use a moving coordinate system based off of that just to make things easier to process. Well, on top of that, while we won't get into the crazier stuff in here, a lot of the times we want to be able to break down our vector into little individual, like, hey, this is a length of 1, 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 this is a length of 1. So you can just go 1, 2, 3, 4, 5, 6, 7, or 6 and some change if it doesn't come out to a whole number. Because maybe we just want to keep moving on that direction. Maybe we want 2v, and it would just be a little easier having some unit vector in the direction of our vector already instead of just using the i's and j's. So that's what a unit vector in any direction does for us. It allows us to make a length of 1, but maybe pointing that way, or maybe pointing this way, or maybe pointing that way. A unit vector is just a vector with a length of 1, but now we're saying instead of just pointing it in the x direction or the y direction, let's let it point wherever it wants to. All right, so given a vector v, I'm going to do it in bold this time, maybe. There we go. You know what? It doesn't even look that bold. No, I'm not. Given a vector v, now it looks bold. Make a unit vector in the same direction following calculation. And we have a symbol for this. A new symbol, it's a little hat. So this little upside down V means it's a unit vector. How do we find this? You take the original vector and you divide it by its magnitude. So in other words, this is just the original vector divided by its length. Let's say you had a vector of length 5. If you divide it by its length of 5, you get 1. Let's say you had a vector of length 27. If you divide it by its length, you get 1. Now, I'm not telling you the components of them. The components can be whatever, but if you divide their components by the length, when you actually go and check the math if you wanted to, you would come up with something that has a magnitude or a length of 1, and we will show that by example. But this is a formula. This is a very important formula. This is a very, very important idea in calculus, through differential equations, through complex analysis, getting a vector of length 1 in the direction that we're moving. Because sometimes in the world, once we get moving, we only care about our perspective. So I don't care that I'm moving 3 miles west and 2 miles north. I just care that I'm moving 1.4 miles northwest or whatever the heck directions I just said. And I'm not saying those numbers go together. I'm just giving you an idea. I don't care that I keep moving 3 miles west, 2 miles north, 3 miles west, 2 miles north. My odometer is not representing that. My odometer is representing that I've gone, I don't know, 25 miles in a particular direction. All right, so example 4 actually. Find a unit vector, same direction as the vector u. Doesn't have to be v, it can be w, it can be any letter in the world. Let's have the vector u be 3i minus 4j. Now you might say, well, Mr. Beckner, if a unit vector is represented with this hat, then shouldn't this be 3 with an I hat and then a 4 and then a j hat? That is another way you can write them. Sure, there's nothing wrong with that. That is a fact. But here's our vector. So 3 right and 4 down. So whenever we draw our vector, we're going 1, 2, 3 to the right, going down 1, 2, 3, 4. There is our vector u. But what I want to do is I want to say, all right, I don't care that I went right 3 and down 4. I'm only going to think about my perspective, and I want to know, where was the first mile marker? Where was the second mile marker? Where was the third mile marker? Something like that. And those are not accurate representations. In fact, I will spoil the answer here. It would have been like 1, 2, 3, 4, 5. That's because it's the common 3, 4, 5 triangle. So maybe you're just interested in mile marker position, so that unit vector would help you every time you go 1. All right, so the vector is 3i minus 4j. We need to know the length, and then we're just going to divide everything by that. So the length of u is just the square root of the sum of the squares of the components. 3 squared plus negative 4 squared. 3 squared is 9, 4 squared is 16, the negative won't even matter, so that's the square root of 9 plus 16, which is the square root of 25, which works out perfectly to be 5. this is the length of the vector we were prescribed. So that line right there, if I went right 3, down 4, marked my terminal point, drew my vector, that length would have been 5, which is why I try to make 1, 2, 3, 4, 5 little mile markers. That's it. That's all we got to do is just divide by that number. Just take the original vector, and divide it by its length. This was the original vector, 3i minus 4j. So, sorry, let me leave the notation up there. So u hat, again, the little hat, this upside down v means unit vector. Just take the original vector, which was 3i minus 4j, and divide it by the length, which we said was 5. Most of us like to break this up, so it would be 3/5 I minus 4/5 j. That's it. So if I went, let's say this was 1, 2, 3, 4, 5, that's going to be one whole. So this is 1/5 is what I'm trying to represent there. And then the same thing going down 1, 2, 3, 4, 5. So that would be one whole. We would be going right 3/5 and down 4/5. So this right here is the vector u hat. It's going right 3/5 and down 4/5, which you can see the components here, 3/5, negative 4/5. So this red vector right here, if I drew everything to scale, which I'm not promising I did in this teeny little one, that teeny little bit right there, that would be the unit vector, and I would be able to fit 5 of them in until I got to the end of the actual original vector. Now maybe you go, oh, I don't trust you. How do I know that this is a length of 1? I just have to believe it? Well, you could certainly prove it. If you found the magnitude, which this should be 1 of that vector, it would be the square root of 3/5 squared plus negative 4/5 squared. And you're just squaring these numbers top and bottom, so that's going to be 9 over 25 and a square root plus 16 over 25, which is 25 over 25 in the square root, which is the square root of 1, which is 1. It does work. So by just taking a vector, calculating its length, then divide the vector by its length, boom, that is what's going to give you your unit vector, which again is a very, 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 very critical concept moving forward in mathematics, because we like to often just consider our only perspective, not break it down into components. Again, I've related it to placing mile markers.
All right, just give me 30 seconds to set up the next portion of the video. And here's part 2 of that.
Last thing we did was example 4, just really, really quickly readdressing what vectors are. They're arrows. These are things that have size and direction, not just a size, not just a direction. So the length of the arrow is important. It signifies how large that value is. And there's a lot of math that deals with vectors moving forward in calculus and differential equations, et cetera, et cetera. we have this symbol, the bold or the arrow means that something is a vector. The double lines around it means that that's going to be the magnitude. It's kind of like the absolute value, but we're talking about multiple dimensions and not just one, so it's Pythagorean theorem to get to it. We've talked about how we can take a vector and put it pretty much anywhere we want as long as we don't change its length or direction. And that we like to talk about vectors in standard position. So if they start at the origin, the A's and the B's in front of the I's and the J's tell you how far right and up to go or left and down or whatever. We talked about how it's pretty easy to multiply a vector by what we call a scalar, which is just a regular number. We said you can also multiply vectors by vectors, which there's two methods of that. One we'll get into, one we won't today. Adding and subtracting is pretty much as easy as your third grade math. We showed visually what it means to add vectors. I also showed you visually what it was to subtract them, but I erased it because it's less interesting. We talked about unit vectors being a length of 1 like the I's and J's, but they can be in any direction. And quite often we like to have unit vectors in the direction of what we're already pointing, because then we're thinking about relative to what that vector or us is doing. Not just going right and up or left and up, just going, this much in this direction. So it's like having your own little ruler in the direction of the vector that you're going, instead of having the rulers only on the X and Y axis. There are a decent amount of formulas that you have to memorize from this section as well as the next, like how to get a unit vector. That's one of them. Writing things in standard form, you can argue that's one of them as well. Let me just bump this down. Way down. Okay. So the last thing we do is example 4. So we're up to this. If you're given magnitude of a vector, and the direction, the angle, theta, then standard form vector is, this is going to be your vector v will be equal to the magnitude times the cosine of the angle times the I vector plus the magnitude times the sine of the angle times the j vector. This is an extreme, that someone knocked on my door instead of rung and it threw me off. It startled me. All right, where was I before I got startled? This is a really important formula because sometimes we're given the length of the vector and the direction that it faces, and you're more interested in breaking it down into components. Previously, we gave you the components, and those enable us to find the magnitude and the direction. Now we're going to be given the opposite set of things. We're going to be given the magnitude and direction so that we can label the vector in standard form. So if you wanted to break this down a little further, what this says is your standard form was, ooh, that didn't work. V equals AI plus BJ. So what that says here is that the A, the X component, is the magnitude times the cosine of the angle, and B, the Y component, is the magnitude times the sine of the angle. Think back to the unit circle idea. Think back to when we're talking about grabbing the coordinates on the unit circle to do a sine or cosine. We said sine goes like Y, cosine goes like X. Well, here, your cosine is in the X component, and your sine is in the Y component. The only thing that's different there is you've got these magnitudes, these lengths attached to them. So what's going on here? Why does this work? So we're given this distance right here, which is the magnitude. So this is our vector. If this is our starting point, this is the ending point, the terminal point of the vector. And then we can draw a little right triangle out of that where we call this A and this B. And then, of course, this would be the angle that the vector forms. Now, if this was in another quadrant, it would be a reference angle, but we can go between reference angle and angle quite easily. We've done it many times. All we're going to do is the absolute basic trig on this little triangle right here to prove that A and B are those. So the proof. Okay. Here's the triangle, here's your vector. Again, I put it in a quadrant 1 kind of order, but 2, 3, or 4, it would just be a reference angle instead, which wouldn't be a big change. Well, we know that the sine of theta is the opposite over the hypotenuse, which would be b over that magnitude. If you just multiply both sides by the magnitude, you'll get that the magnitude times the sine of the angle is equal to b, which is this right here. It says that the y component of a vector is the size of the vector times the sine of its angle. Similarly, if we do the cosine instead, cosine of theta, that would be adjacent over the hypotenuse, which is a over the magnitude. It's nothing new, just different letters. Guess what we're going to do? We're going to multiply both sides by the magnitude, so that we get the magnitude, the length, times the cosine of the angle is equal to a, which is exactly what this says. The number one mistake people make here is they swap the sine and the cosine. They just think sines go before cosines. No, sines relate to y's, cosines relate to x's. This leads us into a very important concept of physics when we're talking about things involving angles. When you want to talk about dynamics and statics in an engineering concept, very, very, very important. When we want to talk about static forces, frictional forces, all of those kind of fall into this. When you're like, all right, well, what's the force acting here? You have to talk about your perpendicular forces, your downward forces, your opposite forces. I'm not going to get into that in this course because I'm not a physics teacher, but it's all just the same coin, just different sides. So you've got to memorize that formula that I highlighted. I just don't want to leave it highlighted on my notes. You can highlight it in yours, but I'm leaving it that way. All right. So now we have a way of making a vector, whether we're given the size of the vector and its angle or the components. Because if you're given the components, you can derive the angle from that. All right, so example, what are we up to? 6, 5. And for A, if the length of the vector, if the magnitude of the vector is 6, and the angle is 60 degrees, find the vector in standard form, which means the AI plus BJ form. All right, so we just got to find, some people like to write what the A and the B are if they really, really, really want to. It doesn't have to be done that way, but some people might say, well, A, the X component, would be the magnitude times the cosine of the angle, which is 6 times the cosine of 60 degrees. Now you are allowed calculators at this point. It happens to be that cosine of 60 degrees, we do know, we can figure that out because it's a 30 or a 60 or a 90 or a 15 or a 120, all those angles that we have practice with. And the cosine of 60 degrees turns out to be a half. So that's 6 times a half, which is 3. You need to see that. Here's 60 degrees, here's 30 degrees, 1, 2, square root of 3. Cosine is the 1 over the 2. For the B, the y component of the vector, it's the magnitude times the sine of the angle, which is 6 times the sine of 60 degrees, which would be the square root of 3 over 2. So that's 6 times the square root of 3 over 2. 6 divided by 2 is 3, so that's 3 square root of 3. Now, I didn't say to use any decimal approximations for this, so this is actually the answer. If I give you something with 30 degrees or 60 degrees, I expect exact answers. So our vector, it's just AI plus BJ. So 3 times the I vector plus 3 square root of 3 times the J vector. I did not say round anywhere. If you said, what is 3 times square root of 3? So if you wrote 3i plus 5.2j, that's wrong. 3i plus 5.196j, that's wrong. I never said round. Usually you're rounding. Almost all these problems you're rounding, but I didn't say to round that one, so don't round that one. You know how to handle 30, 60, 45, 15 even. I wouldn't do 15 in a problem like this with an exact answer, because now we're throwing the sum and difference formulas in it as well. I'm not saying it doesn't exist in the real world. I'm just saying I'm not that mean on a test. All right, for B, let's say the length of our vector is 11 this time, just to be annoying with all those absolute value looking symbols. And our angle is 192 degrees. Find the vector to 1 decimal of accuracy. So that time I did say to round it. So if you want to break down the A and the B separately before you just go straight to the vector, you can, but you can just go straight to this and go 6 cosine of 60i plus 6 sine of 60j. That would have worked as well. But I'm just doing it in a more meticulous way. So A would be 11 times this is the x component, times the cosine of 192 degrees, which we're going to round to 1 decimal place. That's 11 cosine of 192. Oh, Mr. Beckner, we can't use 192. Yes, we can, because we're not talking about inverse cosine. I also did not type cosine for some reason. What happened there? I clicked that instead. Cosine 192. I'm going to double check and make sure I'm in the right mode. We're in radians, not degrees, so that would have been a wrong answer. And we can close our parentheses for good measure. And we get negative 10.75, blah, 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 so negative 10.8. The B, the y component, would be 11 times the sine of the same angle. So 11 sine 192. And we get negative 2.28, blah, 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 so negative 2.3. So our vector in component form is negative 10.8i minus 2.3j. Now, I didn't ask you to draw this, but you certainly could if you wanted to. So negative 10.8i would be going left about 11. So if, let's just say this is negative 10.8, we're really going to cheat the system. And then down negative 2.3, that says our vector would be pointing at that. That's a little ugly, isn't it? Let's try harder, go slower. Slow is fast, fast is good. There's our vector. And you can see that that's a pretty good representation of 192 degrees. And the length of that vector would have been 11. So that length right there, if you really wanted to label it, that's 11. And this angle right here was the 192 degrees. Easy peasy, nothing complicated, but if you forget the formula, that might harm you. However, it's not like this is really a crazy formula, because that derivation I did is everything. If you forget this formula, just draw up a vector, make your A and B the x and y components, and then just do this quick little algebra trick. Just write the definition of sine and cosine in terms of this, clear the denominators, because that's a pretty common technique that gets us somewhere, and boom, you get your formulas. I have emphasized over and over and over and over and over how much I'm not a big fan of just blatant memorization of formulas. Sometimes that's all you got. But if there is a logic and reasoning, an A to B to C to D to get you there, that's what math is more about to me. You might not ever use this type of math again in your entire life, but I've taught you, in my opinion, how to think logically, how to put pieces of a puzzle together. I've never thought a traditional algebra course or trig course or calculus course for a student who's not going to do this in the real world. They were teaching that material just to teach them some silly material they never use. It's to teach them a way of thinking. All right, so we did A and B. All right, next up. Given a vector in component form, am I on time? I'm getting close. Given a vector in component form, which means we give you it like this, the A, I, that looks like a J, doesn't it? I plus B, J. To find, this is a semicolon, not another J, that's a semicolon. I know they look the same. To find the direction theta and magnitude, which we've already done this one, just draw a triangle again. I mean, yes, there's a formula for this, and it is magnitude is the square root of a squared plus b squared. Again, that's nothing new. But the angle is going to end up being the inverse tangent of b over a. And I'm going to put a special note here in red. Watch your quadrants. Remember, inverse tangent's only good in quadrant 1 and 4. So if your angle is actually in quadrant 2 or 3, if your vector is pointing in 2 or 3, you might get an answer that's in quadrant 1 or 2, excuse me, 1 or 4, and you would have to just use it as a reference angle and put it in 2 or 3. How do you know which quadrant you're in? The A and the B tell you the needed quadrant. Now, where did that, we know where the Pythagorean formula came from. Where did the tangent formula come from? All right, so again, the hypotenuse I'm illustrating as my vector. So that's its magnitude. Here's your angle. Again, I'm drawing this in quadrant 1, but it works for all quadrants in terms of an image. All right, so we don't know the magnitude initially, so let's not try and use that to find the angle. So here's an angle. Here's two knowns, the A and the B, so let's go with tangent. The tangent of the angle would be B over A. So that says the inverse tangent of B over A is equal to theta, if you just take the inverse tangent of both sides. But again, only in quadrants 1 and 4 will you pick up the true answer. So in other words, if your angle goes left and up, that puts you in quadrant 2. Inverse tangent's going to spit out something like negative 30 degrees. Just take the 30 degrees, make it your reference angle here, meaning that that angle is really 150 degrees. Inverse trig functions always have complications like that. We've seen it time and time again. Is it something that's happening every single problem? No. Is it something that's happening in maybe 10, 20% of problems? Yeah, actually it is. So please be careful with that. The most commonly made mistake on test 3 is not paying attention to quadrants dealing with inverse trig functions. It was an issue with the inverse sine, because that only picks up answers in quadrant 1 and 4. When we were using law of sines, we said we couldn't pick up anything bigger than 90 because of that. That was one issue. It's an issue with vectors trying to find an angle given the component form, because if these components put you in quadrants 2 or 3, this inverse trig function, when you put it in your calculator, it's going to think you're in 1 or 4 instead. All right, I think I got just enough time to do an example before I pause for a few minutes. Example 6. If your vector v is negative 4i plus 5j, find its magnitude and its direction theta. Well, its magnitude we could have done before everything we just talked about. It's just the square root of the a squared plus b squared. Is this good notation? No, it's not, because my negative I don't have wrapped in a parentheses. Because negative square root of positive, so that's the square root of 16 plus 25, which is 41. Now, sure, if you want an approximation of this, it's 6 and some change. What, like 6.4? Man, that's a good estimation. I always was good with those. 6.4. So that's approximately 6.4. I didn't say to do exact, I didn't say to round, and in fact, I actually prefer a combination here, which is why I left those details out. But in my math lab, just pay attention to their instructions. The direction, we said, okay, yes, there is just a blatant formula you can memorize. However, if you conceptually understand trigonometry, if you forget this formula, just draw up your little right triangle. Understand that we have the b and the a. This we might have rounded, so it might not be a good idea to use it. Yes, we can, but it might cause error propagation. Small errors become bigger errors. And then you can say, oh, okay, well, if I know these two, that's opposite, adjacent. Let's use tangent. Opposite, adjacent. Oh, well, I need the angle, so inverse tangent, boom. Nothing new, conceptually. All right, so theta should be the inverse tangent of b over a, which is 5 over negative 4. Now, I am going to have to round this. That is an exact answer, but it's not really a good exact answer because it doesn't describe the true quadrant. So this absolutely must be rounded. Check this out. Inverse tangent of 5 divided by negative 4. And we get negative 51.3. Let's round to the nearest tenth. Negative 51.3 degrees. And someone, I'm pulling out red for a reason, someone might say this is the answer. But think this through. Pay attention. Be careful. My suggestion to you is to draw the vector so you know which quadrant this was really supposed to go in. Negative 4i means you're going left, 1, 2, 3, 4. 5j means you're going up, 1, 2, 3, 4, 5. So here's the point that the vector points to in standard form. That's in quadrant 2. Negative 51.3 degrees means you're going clockwise here. This would be negative 51.3 degrees, which is in quadrant 4. So it's wrong. This is a quadrant 4 answer that we need to convert in quadrant 2. So theta prime would be 51.3 degrees. You just cut the negative off. As long as that's less than 90, absolutely less than 90, you can just take the negative off because this would be negative 51.3 degrees, which makes the reference angle positive, 51.3 degrees. So let's put that over here, which means we'll have to do 180 minus theta prime, which is 128.7 degrees. Yes, that is the actual angle, along with the exact and rounded answers for the magnitude.
All right, and I really wanted to go over the next little bit, but unfortunately it was going to be more time than we would have had left, or at least we would have been cutting it really close. So I decided that we would just end it there. So as you can see, like I said, we finished enough to call 7.6 done. So that will be due in a week on the 20th. I'm gonna make sure that all my MATLAB dates for the next several sections are straight. I believe I already set them up, but I'm just gonna double check myself. So you will go ahead and know what's due when if you check my MATLAB, but when you go to watch the week 8 lecture 2 and the week 9 lecture 1 videos, you'll of course see them there as well as they are assigned. So again, the big important reminder is that on the 15th and 20th, that's this Thursday and the coming up Tuesday, the classes are going straight to YouTube. I'm gonna go ahead and start uploading them this afternoon. So if you wanna get to them earlier, you can. Again, those links will be in the Canvas course directly, or you can find them through my YouTube channel, whichever way you've been going. It'll be available both ways. I did finish checking over everybody's second test results, and I believe I already emailed. Yes, I did. I emailed everyone about that. So pretty good results overall. Keep working hard, keep getting that homework done, keep doing the tests. We haven't had anyone miss a test yet, which is awesome. That's pretty rare to be able to say, so I love it. Hopefully we can say the same about test 3 in the final. So keep up the good work. Again, email me if you have any questions. I do apologize for not being able to hold the Zoom classes live on the 15th and 20th, but again, at least we have this solid backup plan. Again, no substitute needed. You still get the pretty much the same thing that you're used to. All right, so take care, everyone. I will see you again on the 22nd for normal class. Make sure you watch the 15th and 20th, those 2 lectures, the week 8 lecture 2 and week 9 lecture 1, whenever you are able to. Try not to dilly-dally and wait till the last second to do it. You don't want to have to do 4 hours of class all at once, but do what you got to do at the same time. All right, take care. Have a good one.